Today we are going through revision. We are going to start with exercises multiple choices. Which portion of the electromagnetic spectrum is used in a television? The right answer is radio waves. C. Which portion of the electromagnetic spectrum is used in a microscope? Visible light. C is the right answer. Which portion of the electromagnetic spectrum is used to identify fluorescent minerals? Ultraviolet light. A is the right answer. Let's carry on with the fourth exercise. What is the wavelength of microwaves of 3 × 10⁹ Hz frequency? First, let's see what is given. In this exercise is given the frequency, which is 3 × 10⁹ Hz, and the speed of light, 3 × 10⁸ meters per second. So, we have to rearrange the wave speed equation. The wave speed equation is C equal frequency times lambda. After isolating lambda, we'll calculate it and we are going to find that lambda is equal 0.10 meter. So the right answer is C. Exercise 5. What is the frequency of infrared light of 1.0 × 10⁻⁻⁴ meter wavelength? As we did in the previous exercise, we are going to do again in this exercise. First, we have to know what is given. In this exercise is given lambda, the wavelength, and the speed of light. We have to rearrange the wave speed equation. C equal frequency times wavelength. To isolate the frequency out, and then we are going to calculate. The frequency is equal speed of light over lambda. We are going to substitute the values that we have, and we are going to find the frequency is equal 3 × 10⁻12 Hz. So the right answer is D. Let's carry on with exercise number 6. What is the frequency of an electromagnetic wave with a wavelength of 1 × 10⁵ meter? To find this, we first need to know what is given. In this exercise is given the wavelength and the speed of light. We need to rearrange the wave speed equation, which is C equal frequency times wavelength, and from this wave speed equation we are going to isolate the frequency. After isolating the frequency, we will calculate it. So the frequency is equal the speed of light over wavelength. After substituting the values of speed of light and the wavelength, we are going to find the frequency 3.0 × 10⁻³ Hz. So the right answer is B. What is the wavelength of an infrared wave with a frequency of 4.2 × 10⁻14 Hz? As we previously did, we first need to find out what is given. What is given is the frequency and the speed of light. Again, we are going to rearrange the wave speed equation. The wave speed equation, which is C equal frequency times wavelength. From this equation, we are going to isolate the wavelength. Wavelength is going to be the speed of light over frequency. After substituting the values of the speed of light and the frequency, we are going to find the value for the wavelength, which is 7.1 × 10⁻⁻⁷ meter. So the right answer is C. In a vacuum, electromagnetic radiation of short wavelengths travels as fast as radiation of long wavelengths, travels slower than radiation of long wavelengths, travels faster than radiation of long wavelengths, or can travel both faster and slower than radiation of long wavelengths. As we know, as we have previously said, all electromagnetic waves, despite on their wavelengths, travel at the same speed. So the right answer is going to be A. Travels as fast as radiation of long wavelengths. When red light is compared with violet light, both travel at the same speed, for the same reason which we said at question 8. If you know the wavelength of any form of electromagnetic radiation, you can determine its frequency because all wavelengths travel at the same speed, as we previously explained. Exercise 11. The further light is from a source, the more spread out light becomes, so the right answer is A. Snow reflects almost all of the light incident upon it. However, a single beam of light is not reflected in the form of parallel rays. This is an example of what kind of reflection? We have said that if the light rays are not reflected parallel, then we don't have a specular reflection. We have what kind of reflection? Diffuse reflection, because we said that there are two kinds of reflection: specular, when the light rays reflect in parallel, and diffuse, when they don't reflect in parallel rays. So this is an example of diffuse reflection of a rough surface. The answer D is the right one. Question 13. A highly polished finish on a new car provides a what kind of surface and what kind of reflection? Again, if we have highly polished, the surface is going to be smooth and the reflection is going to be specular. Question 14. When a straight line is drawn perpendicular to a flat mirror at the point where an incoming ray strikes the mirror surface, the angles of incidence and reflection are measured from the normal, and the angles of incidence and reflection are equal. So the right answer is A, based on the first law of reflection, which says that the angles of incidence and reflection are equal. Question 15. If a light ray strikes a flat mirror at an angle of 27 degrees from the normal, the reflected ray will be 27 degrees from the normal. Again, based on the first law of reflection, which says that the angles of incidence and reflection are equal, the right answer in this exercise is going to be B. If a light ray strikes a flat mirror at an angle of 30 degrees from the normal, the ray will be reflected at an angle of, let's see this exercise. According to the first law of reflection, which says that the angles of incidence and reflection are equal, we have that the angle of reflection is going to be 30 degrees. The angle between the reflected ray and the surface is 90 degrees minus angle of reflection, which equals 60 degrees. Therefore, the right answer is B, 60 degrees from the mirror surface. Question 17. The image of an object in a flat mirror is always the same size as the object. As we have said, the flat mirrors are the mirrors which we use daily. And then in these flat mirrors, the image is the same size as the object. Question 18. When two parallel mirrors are placed so that their reflective sides face each other, what images are formed? And this is because the image in one mirror becomes the... So in this case, we have two parallel mirrors which are placed so that their reflective sides face each other. So in this case, we are going to get multiple images because the image in one mirror becomes the object for the other mirror. So the right answer is A. Question 19. If you stand 3 meters in front of a flat mirror, how far away from you would your image be in the mirror? The image in a flat mirror is going to have the same distance from the mirror as the object from the mirror. So the object from the mirror is 3 meters, and the distance of the image from the mirror is 3 meters. In this case, we are going to have the answer C, 6 meters. Again, for a flat mirror, a virtual image forms behind the mirror, and the distance of the object from the mirror is equal to the distance of image from the mirror, equal 3 plus 3 equals 6. Question 20. Which of the following best describes the image produced by a flat mirror? The image produced by a flat mirror is going to be virtual, upright, and magnification equal to 1. Question 21. When the reflection of an object is seen in a flat mirror, the distance from the mirror to the image depends on the distance from the object to the mirror. Question 22. What type of mirror is used whenever a magnified image of an object is needed? Convex mirror. For a spherical mirror, the focal length is equal to the radius of curvature of the mirror, to 1/2. Question 24. A concave mirror with a focal length of 10 cm creates a real image 30 cm away on its principal axis. How far from the mirror is the corresponding object? So in this exercise we are going to find the distance of the object from the mirror. To find out the distance of the object from the mirror, we first need to understand what is given. In this exercise is given the focal length, which is equal 10 cm, and the distance of the image from the mirror, which is equal 30 cm. To find out the distance of the object from the mirror, we are going to rearrange the mirror equation, which is 1 over p plus 1 over q equal 1 over f, where p is the distance of the object from the mirror, q the distance of the image from the mirror, and f is focal length. After rearranging this equation, we are going to solve it for p. So 1 over p is equal 1 over f minus 1 over q. P is equal 15 cm, so the distance of the object from the mirror is 15 cm. The answer B is the right answer. 25. A concave mirror forms a real image at 25 cm from the mirror surface along the principal axis. If the corresponding object is at 10 cm distance, what is the mirror's focal length? So in this exercise is given the distance of the object from the mirror, which is 10 cm, and the distance of the image from the mirror, which is 25 cm. We need to find the focal length. Again, we are going to use the mirror equation and solve it for f, for focal length. So 1 over focal length is equal 1 over p plus 1 over q. The focal length is going to be 7.14 cm. So the right answer is B. Exercise 26. An object is 29 cm away from a concave mirror surface along the principal axis. If the mirror's focal length is 9.5 cm, how far away is the corresponding image? In this exercise is given the distance of the object from the mirror, which is equal 29 cm, and the focal length, which is equal 9.5 cm. What we need to find is the distance of the image from the mirror, so Q is equal question mark. We are going to rearrange the mirror equation and solve for Q. So 1 over Q is equal 1 over focal length minus 1 over P, the distance of the object from the mirror. After substituting the value of P and F, we are going to find the distance of the image from the mirror, which is equal 14 cm. So the right answer is B. Question 27. If a virtual image is formed 10 cm along the principal axis from a convex mirror with a focal length of minus 15 cm, what is the object's distance from the mirror? In this exercise is given the focal length and the distance of the image from the mirror. What we don't know is the distance of the object from the mirror, so P is the one which we are going to find. We are going to rearrange the mirror equation and solve for P. So 1 over P is equal 1 over focal length minus 1 over Q, and then after substituting the focal length with minus 15 and the Q equal minus 10, we are going to find the distance of the object from the mirror. The distance of the object from the mirror, P, is equal 30 cm. So the right answer is A. A convex mirror with a focal length of minus 20 cm has an object 30 cm in front of the mirror. What is the value of Q for the corresponding image? In this exercise is given the focal length and the distance of the object from the mirror. What we don't know is the value of Q, so the distance of the image from the mirror. We are going to rearrange the mirror equation 1 over P plus 1 over Q equal 1 over F and solve for Q, solve for the distance of the image from the mirror. 1 over Q is equal 1 over F minus 1 over P. We are going to substitute F with minus 20 and P with 30, and the distance of the image from the mirror, Q, is going to be minus 12 centimeters. So the right answer is B. Question 29. A mirror has an object located on its principal axis 40 centimeters from the mirror surface. A virtual image is formed 15 centimeters behind the mirror. What is the mirror's focal length? In this exercise, we need to find out the focal length, and we know the distance of the object from the mirror and distance of the image from the mirror. Again, we are going to use the mirror equation and solve it for F. So 1 over F, focal length, is equal 1 over P, distance of the object from the mirror, plus 1 over Q, distance of the image from the mirror. After substituting P with 40 and Q with minus 15, we are going to find the focal length equal minus 24 centimeters. So the right answer is A. Question 30. In the diagram shown above, the image of object B would be virtual enlarged and inverted, real enlarged and upright, virtual reduced and upright, or virtual enlarged and upright. The right answer is virtual enlarged and upright, because it depends on the kind of the mirror and the position of the object. In the diagram shown above, the image of object B would be real reduced and upright, virtual enlarged and upright, virtual reduced and inverted, or virtual reduced and upright. Is going to be virtual reduced and upright, so the right answer is D. And here we go to the last two exercises of multiple choices. A parabolic mirror instead of a spherical mirror can be used to reduce the occurrence of which effect? Spherical aberration would be the right answer. And the last exercise: when parallel rays that are also parallel to the principal axis strike a spherical mirror, rays that strike the mirror, the principal axis, are focused at the focal point. Those rays that strike the mirror, space, the principal axis, are focused at points between the mirror and the focal point. So the right answer is close to, far from. So let's read again with the answer. When parallel rays that are also parallel to the principal axis strike a spherical mirror, rays that strike the mirror close to the principal axis are focused at the focal point. Those rays that strike the mirror far from the principal axis are focused at points between the mirror and the focal point. And these were all the multiple choices. In the next video you are going to find the answers for the short answers and the problems. Thank you for watching.